Thank you, Joanna. Thank you, the organizers, for organizing this very nice conference. So I want to tell you about some recent joint work with Brian Akra, Donald Robertson, and Florian Richter, who's right there. Florian will give the next talk by an astonishing coincidence. And so he will talk about a similar topic, but a different problem that we addressed in this topic. And so the overarching question in this project is what kind of infinite configurations do we find in sets with positive density? And so this is a question in Ramsey theory that we address using ergodic theory. So I want to tell you a bit of the story of the problem and then how ergodic theory comes in and helps us study this kind of questions. So I'll start with one of the fan favorite theorems in Ramsey theory due to van der Waerden. I think was published in 1927, and it says that if you color the natural numbers with finitely many colors, let's use A here for the colors, then one of the colors contains arbitrarily long arithmetic progressions. So in symbols, this is what it looks like. A plus B all the way up to A plus KB. These are all the same color, AI. And so shortly after this theorem came up, Erdos and Turan were meditating on it, and they were wondering, perhaps the reason this theorem is true is because one of the colors, or rather the color that has the most elements, will contain the arithmetic progressions. Most elements, they determine should be measured in terms of upper density. So, Erdos conjecture. So if A is now any set of the natural numbers that has positive density, and let me find it here. So we measure the proportion of the first 10 integers that are occupied by A with a clean soup, that's the density. And if the density happens to be strictly positive, then A already contains arbitrarily long arithmetic progressions. Let me abbreviate that. So I'm going to write everything again. A is A to reach. Okay. That just means contains arbitrarily long arithmetic progressions. Okay, so they formulated this conjecture, I think in the 30s, early 30s, and they had to wait until 1975 when Semeredi proved exactly that. He said, that's right. Okay, so I imagine this story is very familiar to most people in the audience. I just put it there to contrast with the story I want to tell, which is about infinite sumsets. And so, like the story about arithmetic progressions, it starts in the late 1920s with a coloristic result. So in 1928, Ramsey proved the theorem that gave the name to the whole field. It's usually formulated, Ramsey's theorem, in terms of finite graphs, but he actually proved an infinite version, which implies as an immediate corollary the following fact. The corollary of Ramsey's theorem and so just to keep the theorem is from 1928. I don't know if anyone bothered to write this corollary. So if we partition the natural numbers, if we color the natural numbers with finitely many colors, so if we partition it into finitely many pieces, then there exists one of the colors, AI, will contain an infinite sumset. So there exists a set of natural numbers, I'll call it B, which is infinite, and such that B plus plus B. So I use this symbol to denote this restricted sumset. 2 such that B1, B2 are in B and distinct. So this thing is monochromatic. Does that statement make sense? So I claim it's an immediate corollary of Ramsey's theorem. So if you know the theorem, you can try to figure out why. If you don't know the theorem, don't worry. This is the result I really care about. So there's probably several questions that people have whenever I tell them this. First question, do we really need this restriction here? And the answer is yes. So I'll take that as an exercise. Exercise 1. So there exists a coloring of the natural numbers. I don't write all that. Let me. It's a coloring of the natural numbers into, say, 3 colors, such that no color. So for no I, let me say like this. Okay, does not contain some set B plus B. Here we would take the unrestricted sum. So this is the exercise to do whenever you get bored with the top. Yeah, you can think about this instead. So another question that is very natural. Okay, we can get the sum of 2 infinite sets B plus B. Can I get the triple sum B plus B plus B, the sum of 3 elements in B that are all pairwise distinct? And the answer is yes, and this follows from Ramsey's theorem if we use it for hypergraphs, which I think he proved that in the same paper. So we actually get as a further corollary that for every k, there exists some color I, there exists some infinite set B, such that representation, the k direct sum of B with itself. So this is just all sums. So like this B1 plus BK. B1 is smaller than 2 is smaller than BK, so they must be pairwise distinct, and these are all in the same column. And another question?
Yeah, so if we restrict, say, those inequalities at all, so like we maybe allow B1 to be equal to B2, but all the other ones have to be different, does it immediately break, or could you maybe try to get a little bit of?
That's a good question. I think as soon as you want any, if you allow any equality there, it already breaks.
Okay.
But yeah, not 100% sure. Yeah, any other questions? So there's another natural question still concerning this result here, which is, so this sumset is all of the same color AI. What about B? Are the elements of B themselves also in the color AI?
So strictly speaking, your K result, you want BIs to be ordered, and then your K equal 2. You don't insist on B1 smaller than.
Well, if you prefer, I can write that.
So this to become special.
Right, so it's special case of this one. But you agree it's the exact same set. Right, so can we make the BIs of the same color? So this does not follow from Ramsey's theorem, as far as I know, but it is true. And I know it's true because it follows from a deeper result due to Hindman, which actually contains all of these in a single theorem. Wait, 70, do you know the year? Sure, thank you. 75 was over there. So if we finitely color the natural numbers, I write this partition, then there exists a color I. There exists an infinite set, which I think I'm calling B today, such that if I take the sum of any finite subset of B, no matter the size, that sum will be in the color AI. So for any, let me write it like this. So AI contains finite sums of B, which I could write down as B union B plus B union B 3 times forever. So this is where we stand for coloring results involving infinite sumsets. And Erdos came along at this point, and he started asking, what's the density version of Hyman's theorem? We have a density version of van der Waerden's theorem. It worked very nicely. Does that work for Hyman? Now, you will say, of course, the set of odd numbers has density 1/2. That's very much positive. And odd numbers cannot contain creatures like this, because B being infinite will have 2 elements of the same parity, and that will ruin things. So Erdos said, okay, the odd numbers are bad, but if we shift them, we get the even numbers, which are good. So maybe every set with positive density can be shifted to contain an IP set. Question. If A has positive density, and there exists some shift T such that A minus T contains the finite sums of an infinite set. Right, so these things are called IP sets. I think I just used this word and it didn't explain. So if I say IP set, I mean this. And as you may have guessed by now, the answer is no. There was an example produced by Strauss of a set A that has density arbitrarily close to 1. No shift of A has an IP set. But Erdos was undeterred, and he made another conjecture. Maybe IP sets are a bit too ambitious, all right. What about going back up here? What about B plus B? So then he conjectured let's call this conjecture 1. Density of A is positive. Then there exists some shift T and the set B such that A minus T contains is some set B plus B. And he made another conjecture, which we will also mention. Let's call it conjecture 2. So if density of A is positive, then we don't need to shift. We can just take not 1, but 2 infinite sets, B and C. So to be clear, I'm always talking here about infinite sets, such that A contains the sum B plus C. So here I have an unrestricted sum and I don't need to shift. But of course I did 2 sets instead of 1. And so a quick remark is that conjecture 1 is stronger than conjecture 2. If I can prove this, then I can take C to be B plus T, and then A contains B plus C. Up to the restriction here, but you can take care of that. Okay, so I need to write here. And so the first result we obtained 3-4 years ago, joined with Richter and Robertson, is that the second conjecture holds. I'll just write A contains B plus A. So this was published maybe 2019. And then last year, we were able to prove the stronger conjecture one together with Krab. So Brian Krab, Florian Richter, myself, and Donald Robertson. We proved the second conjecture. So any questions so far? So these were the results. So now I will tell you a bit about the proof. And in particular about how we use ergodic theory to address any of these questions. These are purely additive combinatorial questions at the moment. The hint comes here from the history I wrote for progressions. I stopped because the board ended, but in the next line, I would have written that Furstenberg came up with a different proof of Semeredis theorem using ergodic theory. And that's also our departure point for proving these theorems here. So what Furstenberg did, he invented what we now call the correspondence principle, which is a way to translate questions about Ramsey theory to questions about ergodic theory. So Furstenberg's correspondence principle right, so it states the following. So given a set A of natural numbers, I can construct a measure preserving system. So it exists a measure preserving system, so T, and in this system there exists a set E that has the same measure as the density of A. It's sort of emulating the behavior of A inside the system, so such that for any finitely many shifts, okay, in 10, the measure of this intersection, E T less than 1 E is bounded from above by the density of the corresponding intersection in the natural numbers. So with the correspondence principle, it's very easy to convert Semeredis theorem into a purely ergodic theoretic statement. But the way Furstenberg formulated it, it's not so clear how to convert those problems about infinite configuration. So what we can prove with this, if we combining the correspondence principle in that form, with an intersectivity lemma due to Bertelson, we obtain a weaker version of the conjecture, which says the following. So we get, or we find a set B. So let me say given A with positive density, we can find a set B also has positive density. Actually, the density of B is as large as the density of A. And for any finite subset of B, we can find a set C, which depends on B prime. It contains B prime plus C. Okay, so we can find B's arbitrarily large finite sets, C's with positive density such that the sum is contained in A.
Can you say what this intersectivity lemma is?
Yes, so so given probability space, and sets A1, A2, AN, so infinitely many sets with, let's say the infimum of the measure of the AIs is positive. So then there exists a set I'm calling B. It's the same thing with density of B greater or equal than that infimum. Let's call it A, such that for any finite set if I intersect the AIs corresponding to this finite set, the measure is positive. So I believe Vitaly gave a talk about this lemma a few weeks ago in the learning seminar, for those who are here. Okay, so I think this was essentially the best, or what we knew about this problem until early 2010s. And the issue here is that, well, we have something very nice, that the summon D has positive density, even though B prime is finite. But this is in a way close to the limit of what this correspondence principle can achieve. And that's because this correspondence principle only sees things that have positive measure. If this intersection is maybe infinite, but of zero density, or rather here, if we have some set which is non-empty but of zero measure, probability space won't see this set at all. And so there's a fact, I will write over there. So Bernard Host, whom I should have mentioned already, he gave another proof of the first theorem here a year after we put our proof out, and in the same paper he gives the following example. So Host, he proved that there exists a set A and with positive density, such that whenever A contains a sum B plus C, the density of B and the density of C, they both have to be zero. It's not so difficult to believe that such an example exists, but it rules out any kind of approach using this version of the correspondence principle. And so what we had to do, we had to use a bit more information that comes out of the proof of the correspondence principle, but it's usually not in the statement, about the topology that underlies this system. Okay, so here's the improved correspondence principle. So given a set of natural numbers, and I know some people here like to talk about Furstenberg systems of sequences, so we could write the same thing with a sequence instead of a set. for this talk, I will just talk about the set. So given a set here, there exists a compact metric space. It's homeomorphism, T. A Clopen set X. An ergodic measure. I want now my measure to be ergodic. On X, a point which I want to be generic, so a generic point. In X. I think that's all, such that A, the set I started with, who hasn't made an appearance yet, is exactly the set of times at which this point A enters my special set B. Oh, and yeah, so I should have said the measure of E is still positive. It's greater or equal than the density of F. So everyone who's seen the proof of this theorem can write the proof of this theorem. But there is a lot more information here that we can now use, and that is useful when trying to handle infinite configurations. We actually needed something even better than this, and the extra assumption does not follow easily from the proof of the usual correspondence principle. We have, well, someone had to work. Luckily for us, the work had been done, so we just quoted some lemma. But so the conclusion we get here is that additionally, the factor map to the Kronecker factor can also be made to be continuous. There exists a continuous factor map to the Kronecker factor. So to be clear, the Kronecker factor means the measurable Kronecker factor. This can be realized as a rotation on a compact abelian group. So it has a natural uniquely ergodic model. And so I want a topological map between my original system and that topological model of the measurable Kronecker factor. So that's the statement. An equivalent way to say this last line, which maybe some people might prefer, is that every measurable eigenfunction is almost everywhere equal to a continuous function. And a bit subtle. I'm not claiming every measurable eigenfunction is a continuous eigenfunction. I'm claiming it's continuous, but it might not be everywhere an eigenfunction, just almost everywhere an eigenfunction. So there are some subtleties here that are not really important for us today. I also want to say one word about what I mean there by a generic point. Yeah, so the way I wrote it, and with the usual definition of generic, this is probably false. But if you replace it with quasi-generic, it's probably true. That's also not what I mean. So we say A is generic. So when I take the average and with well, yeah, and in some Fowler set of the Dirac masses at T and A, this converges in weak star topology to and Fn, and this is Fn goes to infinity, and Fn is any sequence. If you don't know what the Fowler sequence is, it's just a sequence of intervals whose lengths tend to infinity. But the point is, I don't insist, and I cannot insist that this is an initial Fowler sequence.
Sorry, Joel, what is the quantifier on the field?
Did for this?
Right. So I want to be vague, but the way to say it is it's generic with respect to FL. So I don't want to write that.
It says Fn such that.
Yeah, here it is. There exists a Foner sequence as well that makes it.
For the other part, you didn't tell us. For the continuous. The last, additionally, you said somebody worked for it.
Yes, sorry. So right. So we use the result of Frost and Kra they have in their L infinity seminars paper to get this. So the statement is the following: for any measure preserving system, I can find which has a topological model. I can find an extension of this system as a topological system, and this extension is a measure theoretically isomorphic, but topologically extension. And this one has a continuous factor map to the Kronecker. And I can replace Kronecker with any distal system, with any distal. Yeah. Okay, so now with this improved correspondence principle, I can rewrite the conjecture in a dynamical way. So the theorem in a dynamical form. So the theorem we want to prove is that for any system, I don't want to write all the hypotheses again. So let's. Okay, so X is a compact metric space, T is a homeomorphism, mu is a ergodic measure, A is generic. So for any data of that kind and any E open positive measure, there exists a T and a set such that here B plus B is inside the set of times when T and A enters the set T minus T. Okay, so that's now the theorem I want to prove. So I can erase it. So you may complain this was written in a dynamical language, but I still have a sumset here, so I'm still doing combinatorics, which is true, of course. But so here's an observation that will allow me to rewrite that in a more purely dynamical term. So so let A be a set of n, right? So then the statement that there exists B with B plus B in A, it's equivalent to the statement that there exists a strictly increasing sequence. This is the enumeration of this set, such that B of n plus B of m is A for every n smaller than m. Complete tautology. But you will also believe me if I say I can weaken this condition a little bit. So I want now a sequence where this thing happens, but not for every n smaller than m, for every n smaller than m. Meaning for every n, if m is large enough, depending on n, then this happens. Okay, and if we have a sequence satisfying the third condition, you can find a subsequence that satisfies the second condition. And so now I will rewrite the theorem in view of this observation. So given a system E open positive measure. There exists T, and there exists a sequence such that x1, which I will define as the limit of T B of n of A, exists, and x2, which I will define as the limit of T B of n x1, also exists. And more importantly, x2 is in T minus T of B. So I want to convince you now that if I can prove this theorem, then this one follows. So if I can find a sequence Bn where these points can be defined this way, and the x2 is in there, then what happens when I start applying Bn plus Bm to the point A? And if m is much bigger than n, let me draw a picture here. Help.
You want x to be the translator here, right? At the bottom there. You want x2 to be the translator of the set here, right?
Yes. Here's the picture. This is the point A. This is the set E. And here is the point x1. Maybe this is the set T minus T. And here's the point x2. And I apply Bn for a large n to A, I get close to x1, and then if I apply Bm for m very large to x1, I get to x2. And so I think this implies that T Bn plus Bm A is going to be in E whenever so one has to be much bigger than the other. I think n has to be much bigger than. So this led us to define this type of three-term progressions that appear in this system. Because of the origin of the problem, we call them Erdos progressions. So given a system T, this is really a definition that makes sense in any topological system. Erdos progression is a triple of points, or is a point x0, x1, x2, x cross x cross x, such that it exists a sequence T Bn. No, and this. So x0 goes to B1 to x1, and x1 goes to x. So these are slightly different from what you may call Furstenberg progressions, where you take TB of x0, T2b of x0. That would give you the type of three-term progression that Furstenberg can lift into progressions on the natural numbers. These are related, but different. Yes?
So it is supposed to work for all n?
No, this is a n goes to infinity.
Okay.
Okay, and so our goal to prove this theorem is to find an Erdos progression that starts at my generic point A and ends in this shifted E. Okay. So yeah, I want to give a quick example. If we are on a group rotation, X is a compact abelian group. Let's say it's the turns. And T is just rotation by alpha. But alpha is an irrational number. Then the set of Erdos progressions is exactly the set of 3-term progressions inside this group. And if and only if it is a 3-term progression, so it exists some step S. So x1 is x0 plus S, and x2 is. So in group rotations, Erdos progressions agree with what I was trying to call Furstenberg progressions, and they just agree with regular 3-term progressions. And so the main idea of the proof is that if I look in the Kronecker factor of my system, which is a compact group rotation, I can see all the 3-term progressions on there. I understand this very well. And I can certainly find the progression starting at any point A and ending in any set E that I want up to a shift. Yeah, maybe I will explain a shift in a moment. Right, and then I want to show that above this progression, if I look at all the points in my original system that project to this progression, then almost every point above should still be an Erdos progression. So it's very roughly what we want to show. Yeah, let me explain why we need a T. We need a T at the very beginning, that was erased from up there, because the set of odd numbers does not contain B plus B. Turns out, so we need to allow a shift, but it turns out the shift is, in any case, it's either 0 or 1. I don't need any other shift. And we can now see it here, because if I am in a group rotation, and if I have a point in a group rotation and a set in a group rotation, if this is a rotation on 2 points, there is a trouble. But pretty much in any other group rotation, there is no trouble. I can start at any point, create a 3-term progression that ends in any set, or that set shifted one time. So this is maybe an exercise you can convince yourselves of. Okay, so that's why we need this mysterious T here, and that should explain that. So, right, what do I want to say next? I want to, yeah, so how do we do this? So one quick observation is that an Erdos progression I can write here is the same as saying that when I apply the map T cross T to the power T of n to the point x0, x1, this approaches the point x1, x2. So I reduce the two conditions to a single condition just by looking at the product space. But so in the theorem, I still need to come up with this sequence Bn. I cannot pluck this sequence out of thin air, but there's a dynamical device to create a sequence that does something like this. And it's this very natural observation that if x mu t is any measure preserving system, if A is generic, and let's say y is in the support of the measure, well then there must exist some sequence Pn such that Tbn of A is equal to y. And that's because I can take any, converges to y. I can take any neighborhood of y. It has positive measure because y is a support, but A is generic, so some shift of A will enter that neighborhood. Keep doing that, you'll find the sequence. I think I will raise the example. Right, so then the issue is how do I find these pairs of points? So somehow I'm given this generic point A, but I will be looking at the, so I need to find, point x1, x2, and x, such that A x1 is generic for some measure. I'm calling it lambda, and simultaneously x1, x2 is in the support of the same measure lambda. And so the point is, if I take a measure on this measure lambda is in x cross x. If I have a measure lambda on x cross x, which is ergodic, then almost every point is generic and almost every point is in the support. So this will very likely happen. But the product measure, which is the natural measure to put on x cross x, is not ergodic in general, unless x is weak mixing. I could say if x is weak mixing, this becomes rather trivial. But if it's not, we need to look at the ergodic decomposition of the product measure to have ergodic measures we can work with. Okay, and so I think I can just very briefly say that the ergodic decomposition of this product measure of the product measure x plus x is described by the Kronecker factor of x. I will put some quotation marks here by the Kronecker factor. Of x. And because in view of our improved correspondence principle, we knew that the factor map to the Kronecker factor was continuous. Combined with this observation, it leads to the fact that the ergodic decomposition of mu cross mu can also be realized as a continuous map from x cross x into the space of invariant measures where we have the weak star topology. And then this continuity can be used after 10 more pages to find these points and this component. But so I'll stop here. Thank you.
Any questions, comments?
You explain a bit more how T arises?
T?
Yeah.
T came from the correspondence principle. Oh, you mean little t?
Little t, yeah.
Oh, no, sorry. Okay, yeah. So T is either 0 or 1.
Mm-hmm.
I can tell you like this. So T is ergodic, the capital T now. If T squared is ergodic, you can take little t to be 0. If T squared is not ergodic, but A is in the same ergodic component as E, you can take little t to be 0. If they are in the, so T squared would only have 2 ergodic components at most. If they are in opposite ergodic components, you take little t to be 1, sort of to bring A to the same ergodic component as E.
So if you consider longer restricted sumsets, little t would range over longer.
That's right. So yeah, we don't know how to prove this for any longer subsets.
Can I ask a logical question? Do you use is the axiom of choice used indispensably somewhere?
It's very likely used somewhere in some things we quote. Yeah.
Already in Furstenberg correspondence.
Right. So yeah. So it's used, but I think there is because we're dealing with infinite sets. I don't know about the axiom of choice, but for instance, I don't think this could be proved in piano axioms. There's some reason to believe that.
Wait, so it's like with Hyman. If you formulate your eventual result in careful language,
Right.
careful for logicians language, then there is logicians theorem that it has a proof without axiom of choice.
So does Hyman have a proof without?
Hyman, yes, there is. That's exactly the situation for Hyman. Hyman, of course, the best proof uses ultrafield, but because the eventual result can be formulated carefully, then there exists a proof without by general principle.
Okay, so yeah, maybe there exists a proof without axiom of choice. Definitely use axiom of choice. Yes.
I have a related question, which is, I mean, normally I would ask what bounds do you get, but the question doesn't even make sense, right? Like, I mean, is there any way to phrase an equivalent statement that's purely finitistic and that might plausibly have bounds, or is that too hard?
Yeah, most finitistic statements are they're either easy to prove or to disprove that we came up with. We can ask about the growth rate of the sequence P, and so there maybe there's some light, and yeah.
Maybe you need some assumption on A that's stronger than, maybe A might have big gaps or something if it's just positive upper density. But
yeah.
No, if you have positive lower density, it's synthetic, and then it follows from high.
I see.
Right, but still, if you want to control the growth rate of this sequence
No,
B,
the growth rate question remains.
yeah. So this I don't know. There might be some light there.
Okay. If you ask Terry Tower, would he be able to say something involving for an arbitrary growth function f, there exists a, I don't know.
I don't know. He was asking.
You want to ask him to ask Terry.
I think that would be easy.
So it's like Erdos progression.
Yeah.
Other questions or comments?
Can you say us a bit more about why take a restricted sumset and not just a regular sumset?
Oh, the exercise at the beginning.
Yeah.
I'll give you a hint. Take log 2, base n, take the floor, and you take that mod 3. This is a finite coloring of n. I claim none of the colors contains an unrestricted sumset.
Okay, thank you.
Yeah, we can talk more about it. More questions?
Yeah, is there an ultra filter way of doing this? There should be.
So we can interpret the questions using ultrafilters, but we cannot prove. Our proof uses ergodic theory, and we couldn't write this in terms of ultrafilters.
All right.
But yeah, so maybe I can say this. So a set A contains B plus B if and only if there exists an ultrafilter P such that A is in P plus P. So this is a way to use ultrafilters to understand the question.
More questions? So let's thank the speaker again.